So now, after studying about how to take the derivative of a logarithm function, and plus our study on the implicit differentiation, and together with some hopefully the detailed enough review on the algebraic properties of logarithm functions, then a new technique for taking derivative is opened up for us. And that new technique here is being regarded as the logarithmic differentiation. So in your learning at this point, differentiation is an action, is an operation. It means we take the derivative, but now it's a new style. So back in the other lecture when I was saying implicit differentiation was a new style, so here we have another new style of taking derivative, and we call that new technique, new style of taking the derivative here is logarithmic differentiation. All right, and so now I am going to erase the title, and we are going to head into a couple of examples. And now when it comes to logarithmic differentiation, it's a little hard to formulate as a general rule, but we must see it through examples. So immediately I'm going to kick in with some example, and you will get the idea, the generality of that. Okay, and so let me now start out with example 1. And so let's just say we want to find, again, the derivative of our given function, or specifically dy dx. Okay? And at this point in your learning, you have seen the f prime symbol enough, and the dy dx symbol enough, and you have seen often enough that these two are equivalent symbols. But when it comes to these things, using the dy dx, when it comes to when I said these things, I mean when it comes to particularly use the logarithmic differentiation technique right here, using the dy dx symbol would be a little more beneficial. Okay, but so let's look at, and here I don't need to produce part 1, part 2, part 3, but instead I'm about to give 3 separate examples, and they're all about finding the derivative. But I'm going to label them example 1, example 2, and example 3. Every problem stands on its own right there. So, but there will be one generality. So the function we have here is, so find f prime or dy dx. Okay, and here we are given. So now how about our function here is in the equation form, y equals, let's say, x plus 2 over x plus 5, and take the fourth root of all that. Okay, and so when we are looking at this a function like this, at first sight it seems nothing unusual. No, we can just see that there's a quotient inside of the fourth root. Okay, and so as I said, inside, so we can start applying the chain rule. And so with the chain rule, then we're going to eventually, when we come to the chain rule says we take the derivative of the outside. So yes, it does look like we have some outside expression here. And I should have mentioned the inside expression first. So usually, or even though as I said, pretty much anyone is having your own choice of how you can name the inside and the outside function before you attempt taking the chain rule, using the chain rule. But then inside here, a good recommendation could be the x plus 2, okay, over x plus 5, or even though you can find another one. Substituting that for a u, and then your outside function now becomes y equals the fourth root of u, okay? And then we're going to go ahead and proceed with the chain rule by regarding to this fourth root as the 1/4 power. But then the point now, the problem now is that when we apply the chain rules, when it gets to taking the derivative of the inside, just like what the chain rule is saying, taking the derivative of the inside is still going to be a little bit of a messy work. Okay, that's what I would say. And so, and trust me, if you can always pause the video and kind of plan ahead for yourself what would happen if you would follow the chain rule for this. And so here I'm only pointing it out. That's the plan for the chain rule, but I'm not going to actually proceed into it because I can see ahead. like I said, what I asked you to trust me earlier, because I've done these problems for years. And so if you want to go that route, you can take this recommendation and go ahead and stay with the chain rule. But here's the thing, I can kind of see ahead that it will get messy when it comes to taking the derivative of the inside. So how about we're gonna hold on to that plan? Okay, we're gonna hold on to that plan. We're actually not gonna rush into using that plan. Here's the new technique that I'm introducing here. Here's a new technique I'm gonna introduce. And so in the end, a function, but we wrote it as an equation. And so now, since the variable y explicitly written as a function fourth root, and inside of the fourth root we got x plus 2 over x plus 5, it is algebraically legal to take the logarithm, and you have your own choice of taking log. I chose a natural log simply because it's the one that's most commonly used out there, and it's less, you will understand. So I chose logarithm. You can choose log base 10 or log base 5, log base 2, and you will understand a little more clearly why I chose a natural log right here. But once you take a log on the left side, you will also need to take the same log on the right hand side. So basically we took the logarithm, your choice of the log, but we took logarithm equally on both sides of your expression. So your right hand side expression now is going to look as following: fourth root, all that fourth root of x plus 2 over x plus 5 is now being inside of our logarithm function. Okay, but now here's the thing. Doing natural log, taking logarithm operations on both sides of our equation is going to, here's the thing. Recall from the lecture about how to take, or the lecture I was specifically teaching about how to find derivative on logarithm function. Briefly, it's somewhere at the end, I briefly remind through a few examples that with logarithm we can manipulate the algebra of logarithms. So now power 1/4 here, fourth root here can be regarded as a power 1/4. Fourth root, whichever expression is the power 1/4. Okay, and so logarithm now can turn that with properties of logarithm, and this is before derivative. We can turn that into a 1/4 multiplied with logarithm of a quotient. So now the fourth root is gone. Okay, and your left hand side, there's nothing much to be done, so I'm leaving it the same way. Natural log of y pretty much carried on the whole time. So the point now is that the logarithm will keep reducing our expression here. From start pretty complicated, but now it's keep reducing it down, and it turned the fourth root into a coefficient 1/4 in front of the logarithm. Okay, and I'm still not completely satisfied with how simplified this is. So I'm going to step one step further. Recall again that in my earlier lecture, I briefly reviewed about, for logarithms, we have that property where if we're taking log of a quotient, we can turn, so logarithm, quick review right here, logarithm of a quotient, we can turn that into a log of the numerator minus logarithm of the denominator. Okay, and so that's similar, that same property. This is what I'm doing for that equation here. I am going to apply that algebraic property. So natural log of y on the left hand side, nothing to be done. 1/4 on the right hand side, but now I am going to break my expression here, this expression, into a logarithm natural log of x plus 2 subtract logarithm of x plus 5, because here we have a quotient being inside of our logarithm. And again, I need to remind everyone, we are not taking derivative yet. We're just simply breaking it down to smaller logarithm expression. So logarithm natural log of x plus 2 minus natural log of x plus 5. Okay, and so now at this point we have an equation, natural log of y equals 1/4, and yes, it will be a better idea to distribute that 1/4 right here. So our final equation here before taking derivative is 1/4 natural log of y equals 1/4 natural log of x plus 2 minus 1/4 times natural log of x plus 5. Okay, and so this is not our derivative yet, but what we have done is we turned our function from the beginning, and our function was admittedly written as an equation. So y equaled fourth root of all that x plus 2 over x plus 5, and we apply the logarithm operations on that, on top of that, and then with all that here, it's just the further breaking down, and we further breaking down, and so now when we arrived here, when we can no longer break things down, then what I have here in front of me is an equation where x and y are just two equal role variables. Okay, and so in that way, now I'm gonna let the idea of implicit differentiation to kick in. Recall for yourself, I am looking for dy dx, and so in this way, using the idea of implicit differentiation right at this equation right here, here's what I have. I am going, so on my first term, on that term on the left hand side, I am going to take the derivative in respect to x, okay, treating y as the function, but sort of like at this point, let's pretend that y is an implicit function of x. Y is an implicit function of x. Okay, so I'm going to take the derivative on the left hand side, and so the technique about implicit differentiation also says that we can take the same derivative on the right hand side. So 1/4 natural log of x plus 2 minus 1/4 natural log of x plus 5. Okay, I'm now allowed to take also a derivative in terms of x for the right hand side. All right, and so now, we have seen that through through different examples in the lectures when we study about how to find the derivative of logarithms. So each of these terms should come easily. And by the way, derivative laws allowed us to break that into two separate derivatives, term by term. And so now taking the derivative of the first term here, 1/4 times natural log of x plus 2, it gives us 1/4, as the constant coefficient stays the same. Our function now becomes our derivative out of that function becomes 1/x plus 2. Chain rule is little chain rule. There's still something inside of log, but the chain rule says we take the derivative of x plus 2, which is 1. So that takes care of the derivative of the entire first term on my right hand side. And now I am going to subtract. Now 1/4 came out from the coefficient of the previous step, still there. The derivative of this natural log of x plus 5 is going to be 1/x plus 5, and with a little bit of chain rule, it says we need to multiply with the derivative of the inside here. So multiply with 1. So again, to remind everyone about that inside, for the first term, we got x plus 2 being inside of our natural log. So when we took the derivative, that's why it gave me this 1 right here being the derivative of x plus 2. And then when we moved on, when we advanced on to natural log of x plus 5 right here, then we had that part right here. So the x plus 5 right here, taking the derivative, giving me 1. Okay, so that's the right hand side. And so now what about the left hand side? The rule for taking derivative, and now I have to remind everyone again, the variable y is a function of x. And at this point, we purposely see y as an implicit expression of x. It was explicit in the beginning. Right here, y was explicitly defined as a function of x. But now we purposely, as I said, we purposely see y as an implicit function of x, or you can also think that we pretend that y is an implicit function of x. So if that case happens, then here's how we take the derivative in respect to x on the left hand side. This is outer natural log is the outside function, and inside of y is a whole function of x, and we pretend we don't know. So chain rule says taking the derivative of the outside, we have 1/y because it's the derivative of natural log. And now we must multiply with the derivative of the inside. The derivative of the inside is for some implicit function. So we don't know, pretend that we don't know what that is. So that means we're leaving it dy dx. Okay, and now we have successfully used our implicit differentiation technique on our equation just right before that, and now we have finished taking the differentiation. But now we're just a couple more steps before we completely getting things done right here. All right, so I'm gonna get back to my other board, or maybe let me use the space above this because I don't want to erase too much of my other work earlier. So now, so the steps supposed to follow. This is what I'm seeing. So here I have a quotient 1 over y multiplied with dy dx. Okay, so now to solve for it, just like we're carrying on an implicit differentiation problem, and now I am going to solve for dy dx as one explicit expression itself. So here I am to do that. All I'm doing now is to multiply y on both sides. And by the way, each of the term here, let's clean it up a little bit. So now I have a 1 over 4 times x plus 2. That came straight out from the first term of our right-hand side. Okay, and then minus. And then here I have a 1 over 4 times x plus 5. Okay, so that's just everything that came straight out from our previous step. But now, as I said, in this step here, I also multiply the y to both sides, and so on the left-hand side, it canceled out with this y. It leaves behind a dy dx. That other y is now multiplied to the right-hand side. Okay, so now my final derivative is dy dx equals y times all that here, etc., etc., etc. 1 over 4 times x plus 2 minus 1 over 4 times x plus 5 in the denominator. Okay, but still, I'm not quite satisfied with this because you see our equation in the beginning, our function in the beginning had the variable y explicitly written. The variable y was explicitly defined as a function of x, as the fourth root. And so here it is, it's still here, it's still here. This beginning expression of y is still here. So we don't want, so in that way, my reasoning here is that we don't want to see this here as an implicit variable, as an implicit function there, because we already have that written out. So why not? So now I can erase this step, all these earlier work, and carrying on from that step that we're currently at. Now this y variable, so dy dx on the left-hand side, our derivative. This y now can be substituted back with what it was. Fourth root of x plus 2 over x plus 5. And all that there is for my y variable. And now I'm multiplying with 1 over 4 times x plus 2 in the denominator minus 1 over 4 times x plus 5 in the denominator. And then combining these into one fraction or not, look for your instructor's requirements. In my particular example here, I'll just stop right there, okay? Because I don't want to waste the viewer's time to keep looking at how I algebraically work on the algebra steps there. All right, but this is our final derivative. All right, so this is our final derivative. And so that entire problem there was what I call, the technique here started out by taking a logarithm operation on both sides and treat the problem, and then at some point we treat the problem as an implicit differentiation. The advantage of taking logarithm on both sides is that it can break an expression where it contains nasty powers, like fourth root is a nasty power, 1/4 power, and quotient and product into small chunks, small little terms that involves log. So where we can take derivative easier and easier. Okay? So now my choice, as I said earlier when I started into this problem, when I was saying that I chose a natural log as my own choice, because now think about it this way. In one of my steps earlier, okay, when we had the step taking the derivative of natural log of y, and then that equals to 1/4 the derivative of 1/4 natural log of x plus 2 minus 1/4 natural log of x plus 5. Now I'm trying to explain, it's just my own reasoning why I chose natural log over other Okay. So I'm trying to explain why I chose natural log over other logs. Even though you could choose other logarithm, other bases. Log base 2 is fine, log base 10 is fine, log base 5 is fine. The reason I chose log base 2 because, well, what if it was log base 10? What if it was log base 10? If we chose that, then everything is going to look like this. Okay. It's not about the symbol. It's about when we actually took the derivative as the implicit differentiation, then here I'm going to have a, instead of just a simple 1 over y here on the left hand side, I have to end up with a 1 over y, but times natural log of 10. It produces more things for me to involve, to worry about. That's why I chose only natural log. And then same thing with the, and then multiply with the dy dx. Okay. So the left hand side already produces more things for me to keep track of. Once I stay, if I stayed away from my natural log. And then same thing with the right hand side. When I took that derivative, it gave me 1/4, yes, 1/4, multiply with 1 over, okay, the x plus 2, as we already knew, times another extra natural log of 10, and multiply with 1. So in every step here, if we use a logarithm other than natural log, then in every step we have to worry about keeping track of the extra natural log of the base, natural log of the base. And that's why I chose the natural log, simply because I didn't have to worry about these little natural log of the base. Okay, but taking any logarithm for this style, it's the style that we call logarithmic differentiation. Taking any logarithm is going to work just fine. It's going to give you the same answer. All right, so at this point, any viewers who follow along with my example at this point is probably not so convinced. I mean, if we still take a direct chain rule, as I briefly mentioned earlier before I began into the problem, but then sadly I cut it off for that plan right there. Then some viewers might not be so convinced that this technique here wins over the direct chain rule techniques in terms of efficiency. Well, if you're not convinced with this problem yet, in terms of this process here as being faster or easier, then here it comes to another kind of problem where you got no choice other than using the logarithmic differentiation. So now let me bring everyone into example 2 right here. So we are still finding the derivative, but now in example 2, and pretty much the same structure of the problem. And as I said again, I'm bringing up a problem like this so that you will be convinced that there will be a problem out there in your application somewhere here and there where you have no choice of using chain rule or whatsoever rather than using logarithmic differentiation. So what about we have something like this? Why? Or how about to give everyone also a little more experience as well? I'm going to start out with what about when your function in the beginning is written in functional form. F of x equals x, but to the natural log of x. That's what it is. Okay, x to the natural log of x. The idea now, generally speaking, and there are quite a few instances out there, and depending on your applications, there will be the kind of function where you have a, see, in this kind of function I'm seeing, you have some function p of x. And sadly, the function p of x itself is being raised to another variable power. It's at this moment I forgot what this kind of function called. It's not exponential. It's because exponential requires a constant base like e to the x or e to the natural log of x. That's exponential. But this thing here is a function being raised to a function being raised to the exponential another function being in the exponent part of that. So sadly, right now at this instance, I forgot the name, but that's the form, and you will recognize it. But now, how are we going to find the derivative? Please do not go natural log of x times x to the natural log of x minus 1. This is way out. This is not a power function. and it's not the usual the exponential function. So my point is we cannot just apply the the derivative is not simply just x to the natural log of x repeated, because it's not exponential function. Okay, and so now we have to use a logarithmic differentiation. And then here's the thing: when you are attempting to do logarithmic equation, differentiation, before you even proceed, you see our function this time is written in functional notation right here. Highly recommended. It is highly recommended that you're gonna just simply write your functional notation on the left-hand side here to become a variable y, just like in the earlier problem, in the earlier example. And so now this is what I'm doing. So now I'm going to rewrite it as y equals x to the natural log of x. Okay? And so in the end, we don't have to worry about the f prime symbol, but now we will look for the dy dx symbol. But now that's just a little bit of beating around the bush. Similar to what I've done earlier in example 1, I am going to equally take logarithm, and it is hopefully at this point clearly seen why I chose natural log. Even though you could go with, you can go with log base 2, log base 5, log base 10, whichever log that you would like to, but same log to be applied on both sides. And now natural log of x to the natural log of x. Okay, so this is your function. And so now what's the advantage for doing this? The left-hand side, there isn't much to be done, so I'm leaving it there, natural log of y. But the right-hand side, see, the power property of log, again, when we're applying a log on something that has a power, has an exponent, then we are going to bring that entire, so let me quickly underline that here, but we have this it shouldn't be little at all, but we have that power there, that exponential part right there. I am going to multiply that in front as the coefficient. And so now I'm going to have natural log of x. That power that was inside of my logarithm here, I'm going to bring that in front. But now what's left behind for us here is going to be times, and then that natural log here is just natural log of x. Okay? And so really all of a sudden I realized I turned and natural log of x times natural log of x is the same as so that means our equation natural log of y should equal natural log of x being square. And what I was saying in the middle of what I was saying earlier, see, natural log of x times natural log of x is the same as natural log of x all squared. So that's what we reduce our equation to. And now at this point we are ready for implicit differentiation. So the implicit differentiation step now is kicking in, and so every step all the steps we have done so far is only serving that purpose, where we breaking that ugly looking, that scary looking expression in the beginning here down to something that we are familiar with, that we have some rules, some tools to handle derivative. Okay, and so now on the left hand side I am going to take a derivative in terms of x. Okay, and on the right hand side I am also going to take a derivative, it's a square, and we're going to take another derivative in terms of x. And so the left hand side, you have seen that in the earlier example, it's going to be pretty much the same. Here it's 1 over y times dy dx. Okay, once again I see this as y itself is an implicit function of x. How implicit is that? Just pretend that we don't know. We actually already had it. I have to remind again, we already had it. It's here. But even if it's written out explicitly, we don't know much about that kind of function. All right. But now when we brought our equation down to this form right here, where we took equal natural log on both sides, then we now can pretend that these two variables are just equal role variables. And inside of y, there's an entire function that we pretend that we don't know what that is. Implicit function of x. And so now taking the derivative, chain rule says we take the derivative of the outside, and that's why I produced 1 over y. But now chain rule said further that we have to multiply with the derivative of the inside. Pretending at this point, pretending that we only know y is being implicitly defined as a function of x, then we're going to leave the derivative as the implicit derivative here. That's why I had 1 over y times dy dx. And that took care of the left-hand side. And now I am going to move on to my next side right here, to my other side, the right-hand side. So there is now, I purposely wrote quite a few levels of parentheses. We're taking the derivative. But this thing here is pretty straightforward. The little chain rule now can apply. There's the outside function being the square function. And inside of the square, we have the natural log of x function. So now chain rule says, and another thing to remind again, the right-hand side is completely in terms of x, explicitly in terms of x. And we are taking the derivative. We are finding our derivative in terms of x, okay? And so in that way, now I can just apply the usual rules I've learned, everything we have learned into this derivative. Chain rule says I'm going to multiply the 2 down because the outside function is a power function. So now we're looking at 2 times the natural log of x to power 1. Because once we multiply down that power, we reduce the power by 1. 2 minus 1, we're looking at 2 times the natural log of x. But now I need to multiply, according to the chain rule, I need to multiply with the derivative of the inside. The inside is here. All right. And so with that derivative of the inside, now it's going to be what? The rule for taking natural log of x, 1 over x. Okay. And so now all together, now the right-hand side can be written as, see, this is 2 natural log of x all over x. And the left-hand side still remains 1 over y times dy dx. Okay. Please, it's a huge algebra error to cancel out the x and the x here. So I don't want any of my students to fall into that mistake right there. So don't do that. The x here is inside. So because even if I have parentheses or not, I eventually some quarter I keep having students mistakenly cancel the x here with that x. But I have to remind again, just like the sine and the cosine function, natural log is without the x input here. Natural log is not a quantity. So if you cancel the x with that x, and supposedly looking something like this, 2ln, but ln is not a quantity. It's not an expression. It's only an operation. An operation. So without the input indicator here, it's a meaningless thing to write. So don't go that way. Don't cancel the x like that. But now when we arrive at the step right here, now I can just, similar to the earlier example, I am going to solve for dy dx by multiplying both sides by that y variable. So now my final expression is as following. 2 times y times natural log of x over x. Okay? And I'm still not quite satisfied with this final expression of mine, because in the end I still remember correctly that our function in the beginning was y was an explicit function, a function explicitly defined in terms of x. And it's still here. They're still right here. Okay? And so in that way, and now I will, in my final derivative, I will bring back whatever the meaning, the actual substitution of y for itself. So dy dx now is going to be 2 times y, but the function y for y itself is x to the natural log of x. Okay, and then I'm gonna multiply with natural log of x. Okay, and then all of that over x. And this is how we have found our derivative for this scary looking function. Okay, and that's the whole point of using the logarithmic differentiation. We use logarithm. We apply logarithm on both sides of our equation and then we took advantage of the properties of logarithm to break it down, break our expression down, especially when it involves crazy powers like that, crazy exponents like that, and it breaks it down into smaller chunks. Not necessarily more simplified, but at least it's simpler chunks and easier to handle on each one by one. Okay, and that's the whole technique. And then after we broke it down at the point where we cannot any longer we can't any longer break it down, then we're going to start using implicit differentiation. Okay, so actually three major steps. Apply logarithm on both sides. That's the first step in the technique. Okay, and then break it down using the log properties. So those first two steps are for sort of like the algebra. And the third step is to apply implicit differentiation. Okay, so three major steps right there to remember in terms of your operating with your logarithmic differentiation. And now, before we completely finished with our lecture here, let me bring up another example. And so here we are at our example 3. All right, so in our example 3, again, we are just going to find the derivative, either f prime symbol or dy dx. And as I have explained earlier, in this kind of problem, taking logarithmic differentiation of a function, using the logarithmic differentiation of the function, then this symbol is going to be a little more beneficial for using it. Okay, so our function here, we want to find dy dx, and given that our function is about y is equal to, I have x to the 8th times x minus 2 to the 12th power, and then we're looking at divided that product there by x squared plus 6 to the 7th power, for example. Okay, and so when we're looking at something like this, then the quotient rule and the product rule, as a combination of those two rules right there, will get the problem done. But forget about it. Something like this, I am personally not patient enough to go through with the product rule and the quotient rule applied in here. And it's going to make the problem for sure messier. Okay? And so in that way, I would see that, and after we've learned about logarithmic differentiation in the two previous examples, then now it's a good place here again to apply logarithmic differentiation. So right from the beginning of our problem here, step 1, as I mentioned and concluded earlier, then I am going to take the natural logarithm. It's a choice of the log I'm using. However, it gave me the advantages of doing that. So I'm taking natural log of y. And on the right hand side, in the meanwhile, all that expression there, x to the 8th times x minus 2 to the 12th power over x squared plus 6 in quantity to the 7th. Okay, I'm going to take a natural log. I'm going to take the natural log operation on that entire expression. And so now, that means, and at this point, after taking the logarithm equally on both sides, and that's taking care of the first step. And the next big step now is to go ahead and algebraically break down this large looking expression. Okay, so a natural log of y doesn't look like there's much we can do about that, so let's leave it the same here. The right hand side here, it's a natural log, and we had a little bit of a product here, but the bigger thing is the product is part of an entire quotient. So now I'm going to, as another reminder, and as you have seen that before already, logarithm of a quotient is the same as logarithm of the numerator minus the same log of the denominator. Okay, and so after that brief reminder, then here I'm looking at natural log of, so the entire numerator here, including that x to the 8th and x minus 2 in quantity to the 12th power, is all in one logarithm. And now I'm going to subtract. I am going to subtract the logarithm of that's x squared plus 6 in quantity to the 7th. Okay, and so now we have two logs now, but at least each of the logs is involving less thing. So we're having less thing to worry in each of our log terms right here. All right, and now I'm going to spend some time erasing my board. Okay, so, and then in the next step right here, then we are looking at, so now natural log of y on the left-hand side. There is not much to be done on that, but the first term, as you can see, the first term here on my board, the first term here is now the logarithm of a product between these two factors where there was some power included. Okay, and so in that way I am going to break that down to logarithm, the same log, natural log of x to the 8th plus natural log of x minus 2 in quantity to the 12. Okay, and then the other term is, and the last term in my, from my previous step is logarithm natural log of the x squared plus 6 in quantity to the 7th. So that's still there. Minus natural log of, so x squared plus 6 in quantity to the 7th. All right, and still at this point, at this current step right here, I got to remind anyone viewing my video that we're not doing derivative yet. We are still working on the algebra of our problem to break it down, and at least each of my log term now is simpler and simpler. Okay, I didn't really simplify, but I turned the expression into something where each little term here is simpler and eventually easier to take derivative. All right, and so now in my next step, again, I'm still not getting anywhere to the derivative yet. The natural log of y on the left-hand side remains the same here since there isn't much to be done. This first term here, natural log of x to the 8th, so now we recall that we can have, we're in the rule for taking logarithms, we are allowed to bring the power to the front. It's not the power rule of the derivative. I have to remind everyone that again. But after bringing down that power, our term that becomes a natural log of x, and just power 1 here. Or usually I might say, you know, just no power displayed here. That means power 1. Then same work can be applied here. Same idea can be applied here. We are now seeing a power 12 here of that units in quantity x minus 2. And so that power 12 I'm going to multiply to the in front of my natural log, and now producing natural log of x minus 2 with only power 1 there. All right, and my last term is going to be the same. Minus, now the 7th being the power of my entire quantity x squared plus 6 right here. This power 7 can be brought out front. So 7 times natural log of x squared plus 6. Okay, so now each term, just a little bit before we advance, but as a reminder, logarithm of a sum, we don't have any particular formula for that. So my point now is that this last term right here is pretty much at its dead end right there. Okay. All right. So now we are going to start taking derivative using implicit differentiation. So that's sort of like the third stage, the third big step in our technique in doing logarithmic differentiation. So the left-hand side, as you have seen throughout two earlier examples, now I don't need to explain too much now. Left-hand side becomes 1 over y multiplied with the implicit dy dx. The implicit derivative dy dx, and then the right hand side, now it's just a matter of taking the derivative in terms of x, term by term. Okay, so first term is easily 8 times 1 over x, and it's just the plain old natural log of x function, so derivative is just simply directly out of the box 1 over x. The next term right here, 12 multiply, but since the expression inside of my log is a little more than just the ordinary x input variable. So now that means we're going to have to apply a little bit of chain rule here. So 12 times 1 over x minus 2, but multiply with 1 because 1 is simply the derivative according to the chain rule. 1 here is the derivative of that inside expression of our current term here, natural log of x minus 2. So x minus 2 gives me that inside expression, that inside derivative being 1. I am going to subtract further. And now 7 as a constant coefficient. I am going to take natural log, the derivative of natural log, which gives me 1 over x squared plus 6. But then the chain rule again says, because we recognize inside of our logarithm function, there's an expression other than the simple x variable. And so now the chain rule says we need to take the derivative. So now the derivative of x squared plus 6 is going to be a 2x. And according to the chain rule, we need to multiply the derivative of the outside to the derivative of the inside. All right. But now at this point, we have successfully found our implicit derivatives. And so now the last step here is to clean up the terms here a little bit and go ahead and solve for the dy dx. So now my dy dx here, to solve for dy dx explicitly, I am going to multiply the y variable to both sides. And then before I multiply the y variable to both sides, how about this first term here can be rewritten as 8 over x to be in one fraction. 8 over x, and then plus, now 12 times this fraction times 1 is simply just 12 over x minus 2. Okay, and then the last term here is 7 times this fraction times 2x all together in one fraction. It is simply going to be 14x all over x squared plus 6. And now that entire expression on the right hand side now is going to be multiplied with our y variable, because from the earlier step, as I said earlier, we were going to multiply y from both sides, and doing that it will cancel out the y, and that's why consequently in this current step right here we no longer see the y variable, and then that y variable is being multiplied to the other side. All right, and then at this point I'm not quite satisfied with the way how it looks right now, because I don't want my final answer to be involve a y variable, because we have to remind ourselves in the very beginning of the problem, our function was expressed explicitly as a function of x. So why do we have to leave? So in that way, we have no reason to leave the y variable here in our problem. So now we can just, and recall for yourself, if y is equal to all that right here, then that is our substitution expression. All that on the right hand side here can be, all that here, all that expression there can be resubstituted into our final derivative. So now back in my current step, and I'm very close to being done right here. My final derivative is going to be x to the 8, and I do believe I'm very short at space now, so let me erase this step up here so that I can write my final answer for the problem. And so now in that way it looks like I'm doing a little bit backward step right here, because I'm going bottom up. But so dy dx now is going to be, so the expression y now it becomes x to the 8th times x minus 2 all to the 12th power over x squared plus 6 to the 7th. And all that there is to be multiplied with x over 8 plus 12 over x minus 2 and minus 14x over x squared plus 6. And that is how we are done with our derivative. And that's how we found the derivative for this particular function. Such a scary looking expression, such a scary looking function, other than being explicitly defined here. If we directly apply all the basic rules we learned, it's going to be a very messy work right here. But now look at how useful that is once we apply the logarithmic differentiation technique into our problem.